Today on lesson 5.2, we are talking about co-function trig identities. So co-function trig identities are when, imagine if you had a triangle, okay, and it's a right triangle, and we have theta. A co-function trig identity is alpha, and since all triangles add up to 180 degrees, if it's a right triangle, then all of the other two angles have to add up to 90 degrees. So all co-functions deal with the fact that this, let's call this alpha, it could be represented as pi over 2 or 90 degrees minus theta. And likewise, theta can be represented as pi over 2 or in 90 degrees minus alpha. So keeping that in mind, if we were to find the sine of theta, right? If we were to find the sine, so that would be, if I called this x and y, our sine of theta is x over y. But if I wanted to do sine of pi over 2 minus theta, well, that is my co-function. That is the other angle here. So that's my co-function. So this is, and the sine of that would technically be, let me call this z. That would technically be z over y, right? So this is the same thing as saying sine of alpha, but that is z over y. But what is z over y? Z over y, if we put it in terms of theta, z over y for theta is our cosine. So we can say sine of 2 pi minus theta is technically the cosine of theta. And thus, that's how we get our cofunction values. So sine is to cosine. So cosine of pi over 2 minus theta is sine of theta. And tangent is to cotangent. So tangent of pi over 2 minus theta is actually our cotangent of theta. And then our cosecant matches up to our secant. So secant of theta, and our secant of pi over 2 minus theta is cosecant of theta. And likewise, cotangent of pi over 2 minus theta is our tangent of theta. And so that's how we get our cofunction trig identities. Let's put some of this to use. So let's say we had a sine of pi divided by 2 plus x, and it equals, and we want to set it equal to cosine of negative x, and we want to prove that really quickly. Well, I want pi of 2 minus x. Well, that's simple. I can use a double negative, so that means that sine of pi over 2 minus a negative x, and that will give me, well, now we have pi over 2 minus a theta being negative x. That equals cosine of negative x. Let's try another one. Let's say we had a secant squared of x minus cotangent squared of pi divided by 2 minus x, so this is already given to us, equals 1, and we want to set it equal to 1. So I can prove that it equals 1. Let's think about what we have first. Cotangent squared of x is the same thing now as we know from our cofunction tangent squared of x. So this can be simplified to say secant squared of x minus tangent squared of x. And as we already should remember from our Pythagorean identities, 1 plus tangent squared of x equals secant squared of x. So let me write that down. 1 plus tangent squared of theta must equal secant squared of x or theta. That also means we can rewrite this and say that secant squared of x minus tangent squared of x must equal 1. So this automatically equals 1. Let's do a complex one here. What if we were given a complex trig identity? So let's say we are given 1 plus sine of theta all over 1 minus sine of theta, and it equals 1 plus sine of theta all over the absolute value of cosine of theta. How do we prove one way or the other? I'm gonna work with the side with the square root sign, because I feel like I can get that to equal 1 plus sine of theta over the square root of cosine of theta more easily than I can do the other way. Both ways are possible, but let's manipulate the square root of that 1 plus sine squared of theta, 1 minus sine squared of theta. What I'm going to do first is we cannot just square it. We cannot square it. We are going to manipulate whatever's underneath the square root with the tools that we have. So I'm gonna manipulate. I know that the numerator here is 1 plus sine of theta. So I'm gonna multiply the numerator and the denominator by both 1 plus the sine of theta. So this is 1 plus the sine of theta. This gives me 1 plus sine of theta squared in the numerator, and in the bottom it gives me the difference of perfect squares. So this becomes 1 minus sine squared of theta. And if I simplify that further, 1 plus, if I square root, right, the numerator and the bottom, if the numerator, if I square root that, that becomes 1 plus sine of theta. However, in the bottom, I still have the square root of 1 minus sine squared of theta. And I know that 1 minus sine squared of theta is equivalent to the cosine of theta. So 1 plus sine of theta must be the equivalent to the square root of cosine squared of theta. Square root of cosine squared of theta is just cosine of theta, but we are going to give it the absolute value, because remember, when we square root a function that we don't know the variable, it could be positive, it could be negative, but we're going to assume it has to be positive in this case, because we're dealing with the Pythagorean identities, and those comes with the distance formula, so they have to be positive. So we have 1 plus sine of theta must equal the square absolute value of cosine squared of theta. And there we go. We have proven our trig identity.